Our next topic is recursion. This is very important topic because a lot of functions or the procedures can be written using recursion. That is, they can be written as recursive functions. So let us learn about them. So what are the topics that I am going to cover in this video? What is recursion? Example I will take and explain by tracing of that recursion, how to trace it, how to know the output of a recursion. Then a recursion uses stack. So what does it mean? How it uses a stack? That I am going to explain you. Then also I'll show you how to find the time complexity of any recursive function. So let us start with what is recursion. Now before showing you recursion, first of all let me remind you one thing. Here I have one example program, that is main function and one more function called function fun. And this main function is calling this function. So how this function call is made, how it works, let me remind you this. Already I have explained you in my previous video. Let us look at it again. See, once I start executing my program, it will start executing from main function. First it will execute the first statement, then second statement, then the third statement is function call. It goes to this function, enters inside, execute first statement, second and third statement. Once it has finished, the function ends and the control come back to the same line, that is third line. If any more operations present in this line, they will execute. Otherwise, it will execute fourth line and fifth line. What does it mean by any other operations? For example, this function is returning something, and here I have written multiplied by 2 something. So the value of that function has to be multiplied by 2. So this multiplication will be done once the function has returned here with some value. Assume that that function has returned 10. So 10 into 2 can be done only if this function has returned the result. So once again quickly, program starts, first line, second line, third line, control goes here, first, second, third, function ends, control returns, anything pending that will be done, and then remaining statements. This is the important point that you should remember for understanding recursions. So let me explain you next about recursion. Let us look at a general form of recursion. So here I have an example. This is a recursive function. So what does it mean by recursive function? A function is calling itself. So if a function is calling itself, then it is called as a recursive function. So a function, inside that if you see, it is calling itself again. So this is a recursive function. Then one important thing inside recursion is, here you can see that this is a base condition. Condition is there. So there must be some base condition that will terminate recursion. There must be some method to terminate this one. Otherwise it will go into infinite calling. It is just like this. First we call the function first time, then it will call itself, again call itself, again it call itself. So repeatedly it will be calling again and again. So there must be some condition at which it must stop. So in this example, this will call itself if the condition is true, or it can stop if the condition is true. Whatever it is, at some point it must stop. So here if the condition becomes false, it will not call further and it stops. So finally, let us look at it again. A function calling itself is called as recursion, and inside recursive function there must be some condition which will make the recursion stop, terminate. So in my example, if the condition becomes false, it will stop. That's it. So let us take some example of recursive function and study how it works. Let us look at an example. Let me explain you the example. I have a main function which is having some value and calling function fun1 by passing that x, and function fun1 taking parameter n, and if the condition is true, it is printing and then calling itself. I have used a C language code here. So it's printing and again calling itself for a reduced value of n. If whatever n is, suppose n is a 5, then it will call itself for 4. So if I am passing 3 from here, what will be the result? How it works? Let us trace this recursive function and check. Now tracing. How to trace a recursive function? Recursive functions are traced in the form of a tree. So let me start tracing this one. See, inside the function there are two steps that it has to perform if this condition is true. First step it has to print, second step it has to call itself by passing n minus 1, and this it has to do only if n is greater than 0. Let us start. From here I am calling function fun1 by passing x, that is value 3. So here fun1 by passing 3. So first time it has got 3. 3 is greater than 0. Yes. First step, print n. So first step is print 3. Then what is the second step? Call itself again fun1 for 3 minus 1, that is 2. So it will call itself again by passing fun of 2. See, inside the function there were two steps. Both the steps I have completed. First step was printing and the second step is call. So printing is nothing but the output. So what is the output I got so far? Output is 3. Then what about this? It's a call again. Whether this call has finished? No, it has completed first line, second line. It has not yet came out of the function. It has not yet came out of the function. It has to come out. But it is calling this one. So let us execute this. Fun of 2. Again start. 2. 2 is greater than 0. Yes, 2 steps. So the first step is print 2. So the output 2. Then call itself for n minus 1. So fun of 1. Now still this call has not finished. It has printed and it has to call this one. So again a new call, fresh call. Again a fresh call. So that fresh call is fun1 with 1. So fun1 with 1. 1 is greater than 0. Yes. So perform two things. First step, print 1. So in output we get 1. Then the second thing is call for 1 minus 1. So fun1 of 1 minus 1 is 0. Now fun0, fun1 of 0, n, that is 0, greater than 0? No, it is not greater than 0. It will not enter inside, so it will not perform these two steps and it does nothing. So no printing and no calling, and it will not enter inside and it will come out of the function. So this call doesn't do anything. So there is no further calling. Then what it has to do? It will go back to the previous function and come out of the function. So this function finishes. It go back to the previous function that is in this line and come out. Afterwards there is nothing remaining, so it will simply come out and go back to this function and comes out of this one. Then it will come back to main and terminates. So from this call it goes back to the previous call and then previous call, just like the way just now I have shown you how a function terminates and it goes back to the place from where it was called. So this is a tree and this is called as tracing tree of recursive function, and this is the output. Now I will take one more example and show you. So this example I'll just move it aside, then I'll use this portion for showing you next example. Now I have one more example of a recursive function. This is more similar to the first one. Let me compare them and show you. If you check the main function having variable x and calling function fun1, here also main having variable x and calling function fun2. Inside fun1, it is taking parameter n and n greater than 0, two things are done. Here also taking parameter n greater than 0, two things are done. But the difference is, here it is printing and then calling itself. But here, first it is calling itself, then printing. Then what will be the output? So let us trace this one. So this is a minor difference between these two functions. Let us trace. So from here I start. First main function is calling this function fun2. So by passing value 3. So first time function fun2 will be, this is 3. 3, n is 3, so 3 is greater than 0. Yes, so first statement is what? Call itself for n minus 1. Second statement is print. So first statement, it will call itself for fun2 of 2. N is 3, so 3 minus 1, 2. Then what about the next statement, printing? It will not be done. First, this call has to finish, then only it will print. So let us take this call. Let us finish this one. So it will call itself again with n equal to 2. 2 is greater than 0. Again, 2 steps. So first step is call with n minus 1. So n is 2. So it will call itself for fun2 of 1. And second statement, it will be done after this first statement has finished. What is the first statement? Fun2 1. 1 is greater than 0. So call itself for n minus 1. So again next call, fun2 of 1 minus 1 is 0. And printing, that will be done afterwards. First this has to finish. Now fun of 0, that is fun2 of 0. 0. 0 is greater than 0. No. So it will not enter inside this if block. And it will come out. So it does nothing. So this call with parameter 0 has terminated. Now once this call has terminated, the control should go back to the previous call. So previous call was this one. It was called from here. So it will go back to this function call in this line. This line was this one. So this has finished. Now the next line is print n. So what is n value? 1. So it will print 1. So the output is, first output is 1. Then it will go back to this previous call. And second thing that is remaining here, that is printing. Printing it has to do. So the value 2 is printed. Then this will come out of this and finish. So this call finishes. It goes back to the previous call. In that call, it has completed this fun of 2. You can see that this complete fun of 2 is in deep, it is completed. Then the second statement, print n. So the value of n is 3. So this is 3. So this is the output of this function. So you can see that the function values are 1, 2, 3. And here the output was 3, 2, 1. Now let us compare them. In this function, first the printing was done and the recursive call was made. Print and then call. Print and then call. Print and then call. But here, first call is made, then printing is done. So first call, then call, then call, then call. So again now return back. Print, return, print, return, print. So here printing was done at calling time. Before the function is called, printing was done. But here printing is done at returning time, when the function is returning to the previous call. So at the returning time, printing is done. And the difference here is printing is done after the function call. So that portion will be done at returning time. So I have shown you the differences between them. Now let me take one example and show you the differences among them. See, suppose there is a room and there is a bulb in a room and there is a door. And from that room, you can enter into one more room. This is the door for it. And there is a bulb fixed in this one. And one more door. There is a bulb fixed in this one. This is room 1 and room 2 and room 3. 3 rooms and each room is having a bulb. Now, if I give you the instruction saying that switch on bulb, second step is go to next room. So these are the 2 steps if I ask you to perform recursively. So there are rooms like this, right? So nested room, room inside room. Now, if I make you stand here and ask you to perform this recursively, then what you will do? Let us check. You will switch on bulb, first step. Second step, you will go to next room. So the first bulb that you have switched on is 1. Let us call it as output. Then you will enter into next room. Then here what you will do? Again recursively, so switch on bulb. So you will switch on second bulb and then go to next room. You will enter this next room. Then in this room again first step is switch on bulb. So you will switch on third bulb and go to next room. There is no next room further. So it was more like a recursive call, a function calling itself again and function calling itself again. Now this is termination. There is no next room. What you will do now? you will definitely come out of those rooms. Your work has finished. So from third room, you will come back to second room. Now, will you do anything now? No, you will simply come out. You will come out in the first room, then you will come out of the first room also. So third to second, second to first, then you will come out. And you simply come out. Nothing you will do. So it means first stage was you were entering in. So it was just like a calling. And after you have finished this one, you cannot go further. So you'll return back. So this is returning. So you have gone through two phases. One is calling phase, other one is returning phase. Or I can say that this was ascending and then descending. So you were going to next, ascending. Then you came back and back. So descending. So you have done ascending and descending. And at descending time, you have not done anything. Now, I'll give you one more example. First step is go to next room. And second step is switch on bulb. These are the two steps. I have changed the order, you can see. Go to next room, then switch on bulb. Now let us see if these are performed, then what will be the result. If you are here, then I have given you two instructions. Go to next room. Then second step is switch on bulb. So first what you will do, you will not switch on bulb. You will go to next room. Then there, again the first step is go to next room. So you will go to next room. There, again the first step is go to next room. So there is no next room. There are no rooms further. Then you will perform second step. Switch on bulb. So the first bulb to be switched on is third bulb. Then definitely you will come back to the previous room. And in this room you will switch on second bulb. And you will come back to the first room, switch on first bulb. That's it. So I have two different versions of steps here. In first set of steps, switch on bulb, go to next room. So the bulbs were switched on in this order, 1, 2, 3. So where is the recursive call? This is the recursive call. First perform the operation, then the recursive call. Here, first the recursive call, then perform the operation. So the main important thing that I have to show you here in recursion is that recursion has two phases. One is calling phase and the other one is returning phase. So bulbs were switched on while going, bulbs were switched on while returning. So if you see this recursion, print and then call, switch on then go to next room. So this is same as that one. And if you see this one, go to next room then switch on. So here in this example, first go to next room, that is make a call and then print. So this is similar to this one. So finally I can say that recursive functions are just like a rubber band. If you stretch a rubber band, pull it, so next. If you release, it will come back. So same way, recursive function call and then return. So there are two phases. So that's how these are compared. But one thing that may confuse you, just let us look at this one. See, the first value was 3, 2, 1. So the printing was 3, 2, 1. But here the room numbers are 1, 2, 3. Don't compare this with that one. Just understand the procedure, how it is working. Otherwise, I can change the room numbers 3, 2, 1 also. So the output will be similar to them. So the important thing that we have learned here is that recursion will have two phases. One is calling phase and one is returning phase. Now I'll write a general form of recursive function once again and show you. Here I have a function, a recursive function. It is calling itself. There are three statements. First statement, there is something, and then it is calling itself, and there is one more statement. So the question is, when this statement will execute? This will execute at calling time. And when this statement will execute, it will execute at returning time. And if anything is there followed by this function, then that will also execute at returning time only. If any computations are there, any more things are there. So that's it. So from this, like you can take it as a formula. In a recursive function call, before the function call, if anything is there, then that will be executed at calling time. After the function call, it is executed at returning time. So we can call this portion as ascending and this we can call it as descending. So recursive functions have two phases, that are ascending and descending. So the main important thing that we have learned now is that a recursion will have two phases. Let us compare recursion with loop. Loops are repeating statement. Then what is recursion? Recursion is also repeating. See a function call, then again it is calling, again it is calling. So is it not repeating? Yes, a recursion is also just like repeating. But the difference is a loop will have only ascending phase, but a recursion will have ascending as well as descending phase. So that is the strength or power of recursion, that you can utilize or exploit it for writing code easier. So these two phases are there. So the descending is there only in recursion. So that's all. I end here in this video. Then in next video, I'll show you how stack is used in these two recursive functions, and also I'll show you the time complexity. So we'll continue with the same functions in the next video. Now let us look at how recursion uses stack. So I'll take this first example and show you how the stack is utilized. Now already we have seen this model of memory, that the memory is used by dividing into three sections. One is code section, and here I show stack, and this is heap. Now in my program I have two functions, that is fun1 and main. So the machine code of those two functions is already there in code section. Now let us run the program and see how the stack is created. See, the program starts executing from main function. So the first function is main function. In that main function, this is the first statement, that is X is created. So an activation record for main function is created, and it will have its own variable, that is X, having value 3. Then the very next statement is fun1, a call to function 1. So once the function 1 is called, it is having just one variable, that is n. This is the only variable. So activation record for that fun1 is created, and it will have that variable n, and this value x is passed to that one. So it will be 3. So this is for main and this is for fun1. I'm showing you line by line how it is working. Just let us look at it once more. See, the program start executing from main function. The very first thing is x. So activation record for main, and x is created. The value is 3 and the function is called. And that function is having just one variable, that is n. So activation record is created for fun1 with variable n and having value 3. Let us continue. If n is greater than 0, yes, this 3 is greater than 0. Then printf. So as per the tree already we have seen that a 3 is printed. Then the next call, function fun1 is called once again with a reduced value of n, that is decremented value n minus 1. So that function is called again. So once the function is called, we know that activation record will be created, and in that again variable n, and that will have the value 2 this time. This is also activation record for fun1, and this is the second call. Now in that second call, again it checks if n is greater than 0. Yes, 2 is greater than 0. So printf. So 2 is printed. The next line, call again with n minus 1. So right now n is 2. So again a new call, again an activation record is created, and variable n is created with value 1. And this is again a call for fun1. Now again, if n is greater than 0, yes, 1 is greater than 0, print 1, 1 is printed. Then again call fun1, with reduced value, decremented value, n minus 1. So again an activation record for fun1 is created, and it will have the variable n, and that value is 0. This is a call again for fun1. This time, as n is 0, when it calls again, n is greater than 0. So no, n is not greater than 0. It will not enter inside. It will not print anything. Here it doesn't print anything, and it will come out of this conditional statement. So it doesn't enter into conditional statement. So it will come out of the function. And once that call ends, this activation record is deleted. And the control goes back to the previous call. And in that previous call, what it has done, it has called this one. So the next is nothing. So that call will be using this activation record. And that also ends. So again, this is also deleted. It goes back to the previous call. In the previous call, this line is over. So there is nothing remaining. And that call uses this activation record, but there is nothing to do. So this is also deleted, and this is also deleted. Then it come back to main. Inside main, after fun1, there is nothing remaining. So this also ends. So all these activation records ends one by one. So this is how stack is created and utilized in recursion. Now, one more thing. What is the size of the stack? Leaving main function, if you count the activation records 1, 2, 3, 4, so only for that function 4 activation records are created. So size of the stack is 4. And how much memory it's consuming? Each activation record is having just one variable, n. So n how many times? 4 times. So you can see the calls here, 1, 2, 3, 4. Already we have done 1, 2, 3, 4. So already we have done tracing. We have generated a tracing tree or recursion tree. So there are 4 calls. So 4 activation records are created. And at the end of this, it will go back and go back. So activation records are deleted again. So size of the memory consumed by this function is 4 into whatever the size of variable integer is. For value of x, that is n, is 3. For value of n is 3, there are 4 calls. So for value of n equal to 5, there will be 6 calls. So for n, there will be n plus 1 calls. So total n plus 1 calls. So how many activation records? N plus 1 activation records. So we can see that the activation records, number of activation records, depends on the number of calls. So total calls are n plus 1. And what is n? It's a variable. How much memory it's consuming? Now it is integer type. It may be taking 2 bytes or 4 bytes depending on the compiler. So we can say just n plus 1 call. So the total memory consumed by this is order of n. We can mention it as order of n. Why not plus 1 there? See, this is a polynomial, a formula, n plus 1, in that degree of the formula is 1. Highest term is n. So we take n. So we write degree there, order of n or degree of n. So we mention the space as order of n. But actually if you see, it is n plus 1 activation records are created. So from this discussion we can understand that recursive functions utilizes stack. So here internally it takes some extra memory for the stack. So there are memory consuming functions. Recursive functions are memory consuming. So that's all I have explained this one. Now already I have a stack, then just I will show you how this function works. So I will use this program as well as a tree. Then also I will show inside the stack what happens. Let us look at it quickly. There are 2 functions, fun2 and main. Both these functions are there inside main memory. Now let us start executing. Program starts from the main function. So the first variable x. So activation record for main is created and having the value 3 in x. And it will call function fun2. Once the function fun2 is called, activation record for 2 is created. So it means all these are for 2 now. So I'll just change them. So the first call, n equal to 3, this is created. That is this one. This is created. Now n is greater than 0. Yes. Then call again. So again it will call with n minus 1. So a new call will create this activation record with n equal to 2. Then again it will call. Then again it will call. See, because the first statement is call. So it's calling itself every time. When n is equals to 0, 0 is not greater than 0. So it will not enter into if block and come out of the function. Once it come out of the function, this activation record is deleted because the function with value of n as 0 has terminated. It goes back to the previous call. In the same function, it will go back to the previous call where it has finished this one. Now it has to perform this. That is this line in the tracing tree. So what is the value of n it has to print? Now the current topmost activation record is this one, where the value of n is 1, so it will print 1. It will print 1 because the value of n is 1 here. And once it has finished, it will come out and this activation record is deleted. It will go back to the previous call. In the previous call, again it has finished the first line, that is this line. Now it has to do this. So print n. So what is the value of n now? So the topmost activation record in the stack, you can see now n value is 2. So this is printed. So 2 is printed. Likewise 3 is printed and all these activation record ends. So you can see that these activation records are created when the function was calling itself again and again. So this is more like ascending. Now once it has reached the last call, that is where n is 0, so it will start returning. So that is a descending. So while descending, it will utilize these values. So all the values of n are there in the stack in the different activation records. So these values are utilized at returning time. So that's all. This is how recursion uses stack. So both of these functions are almost same, only the difference is that this is first printing and then calling. This is first calling then printing. So the activation record created for these functions will be same only. So that's the reason I have taken two similar examples and I have shown you how the stack is utilized. It will be same in both the programs. The size of the stack and the space consumed by this function is also order of n, that is total n plus 1 activation records are created for function fun2, leaving aside main. This is how recursion uses a stack. Now next thing that we have to study is how to find the time complexity of recursive functions. So I will take just one example, this example, and show you how to find the time complexity of recursive function. So let me tell you the basic concept for finding the time complexity. We assume that every statement in a program takes 1 unit of time for execution. Let me give you the idea behind that one. See, suppose there are some books kept here and you have to move the book and keep it in a shelf or in a rack. How much time it takes? Maybe half a second, quarter of a second. Now for somebody who walks very slowly, it may take 1 second for keeping one book there, one by one if you have to keep. So time varies from person to person. So we don't mention seconds or milliseconds, we say 1 unit of time. Like if you take the example of currency, $1, 1 rupee, 1 pound. So we say 1. But what is the market value? That may be different. So we say $1 or 1 unit of currency. So same way, we assume that every statement takes 1 unit of time. If that statement is repeated multiple times, then you count the frequency, how many times it is executed. So that is sufficient for analyzing our function now. Let us see what our function is doing. It's doing nothing, just printing. So it is printing a value of n. How much time it takes for printing? 1 unit of time. 1 unit of time. How many times printf is written here? Only 1 time. So it is just 1. But this is a recursive function, so it is calling itself again and again. So total how many times it is printing? So let us look at into the tracing tree or recursion tree. Here it is printing 1 time, 2 times, 3 times. So total how many units? 1, 1, 1. So I can say it takes 3 units of time for the value of n as 3. Value of n as 3. So the first value of n is 3. If I make it as 5, then it will take 5 units of time. Then for n, it will take n units of time. So it is just like, coming back to the example, if you have to keep 1 book in the rack, you are taking 1 unit of time. 10 books, 10 unit of time. N books, n unit of time. What is n? Whatever may be. So the time depends on the number of books. So here the time depends on the value that you're passing from here. It may be 3, it may be 5, or it can be anything. So we say the time taken is n units of time. So the time can be represented as order of n. The answer that we got is n units, so the degree of that polynomial is 1, so we write it as order of n. So the time taken is order of n. There is one more method of finding the time complexity using recurrence relation. I will show you how to write recurrence relation and how to solve it to find the time complexity of recursive functions. Now let us find out the time complexity of this recursive function using recurrence relation. We assume that the time taken by this function is t of n. T is for time. If the time taken by that function fun1 is tn, then that total time should be sum of all the times taken by the statements inside. So let us look at the statement. See, there is a statement. This is a conditional statement. How much time it takes for execution? Just 1 unit of time. 1. Then there is a printf statement. How much time it takes? This also takes 1. Then there is one more function call. How much time it takes? 1. As I said, every statement takes 1 unit of time for execution. So this also I have written 1. No, it's wrong. It's wrong. See, that is a function call. So I should know total time taken by that function call. So it is not just a normal statement. It will call again itself, so there is something more behind that one. So I need to know how much time that function call is taking. So let us see closely. When I said this function call total time tn, then this is similar to that one, and this is n minus 1. So yes, this will be taking tn minus 1 time. Yes, this is not a normal statement. There is a function call and it takes tn minus 1 time. Then what is this total tn? I said the sum of all the times taken by the statement. So let's take the sum. So that tn is equals to tn minus 1, the bigger term I am writing first, plus 2. So the total time is tn is equals to tn minus 1 plus 2. So the recurrence relation is tn is equals to tn minus 1 plus 2 when n is greater than 0. When n is greater than 0. What happens when n is equal to 0? When n is equals to 0, it will just check the condition. It will not enter inside and it will come out. So just checking the condition, 1 unit of time. So it takes 1 unit of time. So this is the recurrence relation formed from that function. So the time complexity of recursive function can be represented in the form of a recurrence relation. Now if we solve this using induction method, or also called as successive substitution method, we can get the answer. So let us solve this one. Now before solving this, I should tell you one thing. If you have any constant value here, then let us write it as 1. So that means constant. Now let us solve this. So the recurrence relation is tn is equals to tn minus 1 plus 1. This is the first equation we have. I can solve this if I can know what is the tn minus 1. See, here I write, since tn is equal to tn minus 1 plus 1, then what will be tn minus 1? So if this is n, replace with n minus 1, so this will be tn minus 2 plus 1. So I can substitute this one, tn minus 2 plus 1, in place of tn minus 1. So this I can replace here. So the next equation that I get is tn is equals to 2tn minus 1, tn minus 2 plus 1. So this is tn minus 2 plus 1, and this plus 1 as it is. So this is substituted with this one, and then this plus 1 as it is. So what is this one finally? tn is equals to tn minus 2 plus 2. So let us call this as second equation. Then let us substitute in this place. So what this will be? This will be tn minus 3 plus 1. So if I substitute that, then this will be tn is equals to tn minus 3 plus 1 n plus 2. So this can be written as Tn is equals to Tn minus 3 plus 3. This is the third equation. So I have substituted 2 times. How long I should do this? Let us continue it for k times. So k times Tn minus k plus k. Because this was 3, so this is also 3. If it is 4, then this will be 4. If this is k, then this will also be k. So the fourth equation I got. See, we have to solve this one. So substitute and then substitute, go on substituting until it reduces down to a smaller value, that is n equal to 0, where we know the answer, that is 1. See, when you don't know the answer for a bigger expression, you know the answer for a smaller expression, then break the bigger one into smaller one and solve it. So the same thing we have done. We don't know how much this is, but we know when n is equals to 0, answer is directly 1. So we know that. So we have tried to reduce this and by substituting, and we got this one. Now we say that this n minus k actually has become 0. So on that side I will write down, assume that n minus k is equals to 0. So it means we have n minus 1, that we made it as n minus 2, then n minus 3, and so on, up to what? It became 0. So we assume that this has become 0. So it means, therefore, n is equals to k. So in this equation, if I substitute, that will be Tn is equals to Tn minus n plus n. So at the place of k, I have written n. So n minus n plus n. So I got this one. So this is Tn is equals to T0 plus n. So Tn is equals to 1 plus n. So that's all. I got the answer. Tn is equals to 1 plus n. This can be written as order of n. See, earlier, directly from the tracing tree also I have shown you n plus 1 was number of calls. So yes, I got the number of calls here. And the time taken by this function depends on the number of calls. So yes, it is order of n. So it will be printing for n times and the calls will be n plus 1. That is 1 more than the number of times of printing. Let us summarize the things that we have learned. See, I have shown you what does it mean by recursion, and I have shown you how to write a recursion. I have traced that one, and I have shown you 2 different types of recursion. Then I have shown you how a stack utilized, and then we saw how to find the time complexity. From the tree also I have shown you, and by writing a recurrence relation also I have shown you. And the time complexity is mostly written as order of or degree of, that is order of n. See, I am not using the notations like big O, omega or theta because we have not discussed about them. So I'll give you the idea about these notations at some other time. So it's about to call itself again by passing 3 minus 1. So if I continue next, again the function is called, it has directly entered inside and it is on the conditional statement right now where the value of n is 2. Yes. And here you can see in the debug navigator, the function on the top is 0 and the next is fun again. So function is called 2 times. And then below that is main function. Main has called this fun, then fun has called again itself. So 2 times, this is the second call. Now let us continue further. Printing is done. So value 2 is printed. Again it has called itself. This time the value of n is 1. And you can see that these are 3 calls here inside the debug window. Our main 3 function calls for fun are there. Now 1 is greater than 0, so it will enter inside and it will print this one. Let us proceed. So printing of 1 is done. Then again it will call itself with the value of fun, with the value of n as 0. So this is 0. So these are total 4 calls. So you can count here, above main there are 4 function call. The topmost one is numbered as 0 and so on. Now for this, if I continue, n is not greater than 0, so it will not enter inside this if block and it will come out of the if block. It will not enter inside this if block and also it will come out of this function. So the value when n is 0, nothing happens. Printing is not done and it will not call itself. These 2 lines will not be executed. Let us continue further. So you can see that it has reached the end of the function call and right now the value of n is 0 only. So if I press next step again, then see what happens. It is still there only, but this is for the previous call. And you can see that in the navigator, the functions are reduced by 1. So the function with value 0 has finished. Then what is the topmost function now? With the value of n as 1. Yes, it has gone back to the previous call. Now this is having value 1. Then when it goes back, this will have value 2 and this will have value 3 and so on. And at last it will reach main. So right now it is inside that function call where the value of n was 1. If I proceed further, again you can see that it is standing there. Just there was a blink that has gone to the next statement. So it is back on the same statement because outside if this is the after if it has reached here. So the value of n is 2 and you can see that the number of calls are reduced. Right now it is with value 2. Then below this one, there is one more function call with value 3. So if I continue further, it will go back to this function and this function call will terminate. Let me go to next. Now I'll go to the next step. Again it is standing there only. Just it has blinked and came back to this function call at the end of the function call. And the value of n is 3 here right now. So you can see here in the debugger navigation that above main there is only one function call. Currently we are in that function call with a value of n is 3. Actually this was the first call. So this is how the function is returning one by one. It has called itself again and again. Now it is returning one by one. Now if I continue further, it will go back to the main function call and the program ends. So it's back to this line from where the function was called. Here it has started, so it is back to this function call. So I'll simply finish the program now. So this was the example of tail recursion which we have already discussed on board. So I have shown you how the function calls are piling up on a stack. I will modify the same function into a head recursion by just copying this line. I'll cut it from here and paste it just before printf function. So you can see that first the function will be called, it will be calling it recursively, then it will print the value. So again I will put a breakpoint here upon this line, the first line inside the main function. Now let us run the program and see what the output is. We know the output already, that the output is going to be 1, 2, 3, but let us learn how it is generated. Running the program. Now in the debug navigator, you can see that the starting point is main function, and the main function, it has stopped in that line where we have given breakpoint, and the value of x is not yet initialized, it is garbage. If we continue further, the first line is executed and the value of x has become 3. Now it is about to call a function. And in the navigation, you can check that there is only just one main function, that's all. If we continue further, then this is the first function call. This is the first function call, you can see, and the value of n is 3. Then 3 is greater than 0, it will enter inside and it will make a call again without printing. Yeah, it has came to the line where there is a function call. Now back. Now again a function call. This time there are two function calls and right now the value of n is 2. I'll continue. Again on the function call, recursive call. So it has called again itself with the new value, that is 1. Then 1 is greater than 0, it will enter inside and again it will call itself for 0. Yes, again a new call. So value is 0. You can see that this printf is never executed. So total how many calls? We have passed 3. So for calls are for 3, 2, 1 and 0. 4 calls are there. So inside the debug navigator, you can check that above main function there are 4 function calls. Right now it is in this function call. And right now the value of n is 0, so it will not enter inside if block and it will terminate. So this function will terminate and it will go back to the previous call. See, this is the last line. Now if I press again, now if I press F7 again, it will go back to the previous call. Yeah, it is back on the previous call. It is on the same line from where it has called itself and the value of n was 1. Yes, previous to 0, the function call was 1. Now next line it will be printing 1. Printf, execute. Yes, it has printed 1 and it came out of if block. Now it's about to terminate. Function call with value n equal to 1 is about to terminate. If I continue, then it is back on the previous call. You can see that the call has reduced here. It is back on the call where it was n value was 2. So yes, here it is, n is 2. So then it will print this 2 and go back. So you can see that printf is being executed at returning time. Calling time, there was nothing in this function. So I'll continue execution. Printf 2, then go back to previous call where the value of n was 3, then printf 3, go back to the previous call and it has gone back to the main function and that's all. Function ends. So that's all. We have seen how a recursive function works. We have seen the calling phase as well as returning phase. Let us look at static variables in recursion. We have seen how to trace recursion. We have also seen how a recursive function utilizes a stack. Then what if there are any static variables, how to treat them inside recursive function. So here I have an example function, recursive function. Though there are no static variables right now, without static, this function I will trace it and show you. Then if static is introduced, then I'll show you what should be the difference. First, let us see what the function is doing. I will read it out. I'll explain what these things are. See, there is a function fun which takes parameter n. If n value is greater than 0, then it will call itself with a decreased value of n and also add n. So when this plus n will be done, calling time or returning time? It is done at returning time. Then if the value of n is 0, then it returns 0. And from main function, this function is called by passing a, that is 5. Now to show how they will work inside the memory, I have already taken a diagram for the memory where I am showing code section, both the functions are there. Then how the stack is used, I'll explain you. First of all, I will trace this function for value 5 and show you the tracing tree. First, the function is called for the value 5. So this is fun of 5. And 5 is greater than 0, yes, so it will call this one. So it will call itself for fun of 4 plus this n. So let it be blank here. That will be filled with the value of n. And what is the value of n here? 5. I'll use it afterwards. Then it will call itself for 3 plus 4 should be added. I'll leave it as a blank. Then fun of 2, 3 should be added. I will leave it as a blank. Then fun of 1, 2 should be added. Then fun of 0, 1 should be added, and fun of 0 is 0. This is 0. Now when it goes back, this is 0 plus 1, this is 1, so this will be 1. And the result of this one is 1, plus this is 2, so this will be 3. Then the result of this is 3, and this is 3, so this will be 6. So the result of this one is 6 plus 4, this will be 10. The result of this one is 10 and 5, so this will be 15. So the result of this is 15. So this is the tracing of a function when it is called upon value 5. Now let us see how the activation records are created. Then the activation records for fun will be created. Value of n will be 5. Then value of n will be 4. Value of n will be 3. So this is how stack is created. Every time for each call, a new variable will be created inside the memory, and it will have its value. That is 5, then 4, then 3, then 2, then 1 and 0. So all these values are newly created every time whenever the function is called. This we are aware of local variables of a function. Now I am going to make changes in this function, then we will see how to handle static variables. So I am making modification. Static variable. Integer x whose value is 0 initially, and before calling I'll be incrementing it, and while returning I'll be adding x. So this is not adding n, adding x, and x is incremented and it is static. So first of all, where these static variables are created, they are created inside code section, or there is a subsection of a code section called as a section for global variables and static variables, but I am showing directly inside code section, and the value of that one is 0. Will this static variable be created every time whenever the function is called? No, it will not be created every time when the function is called. It is created only one time, that is at the loading time of a program. So this x will not have multiple copies just like n, it will have a single copy. So all these calls of this function, they will use the same copy of x. So I cannot have a separate copy each time like n. For n, every time a new copy is created, but for x, there is a single copy. Now, what will be the result of this function? For that, I will trace it again. So for that, I will remove these things and I will trace it again. Let us look at the tracing and see how static variable should be handled. For a static variable, it is x, so I should have a single copy of static variable separately. Don't show it in the tracing tree. Now let us start. First time the function is called by passing value 5, so n value is 5. First time fun of 5. Then if n is greater than 0, yes, it is greater than 0, x plus plus, this x becomes 1. Then call itself fun of 4 plus this x will be added at returning time, so use it at returning time, don't use it now. Continue for this call. Again 4 is greater than 0, x plus plus, so this x becomes 2. Call function of 3 plus x should be added at returning time. Then call greater than 0, x plus plus, call itself. So 3 call for 2, x plus plus, then plus this x should be added. Then for this call, again this is 4 and call for 1 plus x should be added. Now for this call, this becomes 5 and call for 0 plus x should be added. Call for 0 returns 0, so the result of this function is 0. Now it will start returning back from here. So this is 0 plus x has to be added. So what is x now? 5. So this is 5. Result of this is 5. Then x should be added. What is x now? 5. So this is 10. So the result of this function is 10. Then plus x should be added here. So what is x now? 5. So this is 15. See, in the previous example, we were adding n. So n was having its own value in each call. So those values were used. But now there is only one single copy of x. So each call will use that same copy, and right now it is having value 5. So that same 5 is utilized by all. So this result is 15 plus 5, so this is 20, then 20 plus 5 is 25. So the result of this function is 25. So that's it. This is how you should handle static variables. If there are any static variables inside recursive function, don't show them in each step of tracing tree. Write them just like a global or outside variable and maintain a single copy of it. So sometimes we need to use static variables also in recursion. So I have shown you how they work. Now, if it is not static, if I take out this variable and if I declare it outside like a global variable, then also the result will be same. So static variable will have a single copy, and even global variable, it will have a single copy used by all the function calls. And those global variables are also created inside code section, and every call will use the same copy, and the result of the program or the function will be same. So in the previous example, the result was 15, but now for 5, the result is 25. So here in printf, result will be 25. So in the coming examples, we will use this recursive function with static variable. In this demo, we'll look at static and global variables in recursion. I'll start a new project, command line tool. I'll give the project name as static global. Create a project. Project is ready, and here is the main function. I will write down the function that I have shown you. Integer is the return type of a function, and the parameter it takes n. Now inside this, if n is greater than 0, return fun of n minus 1 plus n. Otherwise, return 0. This is the function we have seen, which gives the sum of first and natural numbers. Let us take a variable r, and inside this r, let us get the result of a function by passing parameter 5. And I will print the result obtained by that function. %d, only one value, that is r, I have to print. This is the function already we have seen. The value, if we pass the value as a 5, it returns 15. I will directly run the program, and let us see what is the output given by this program. Here the output is 15. Yes. Now I will modify the function. I will introduce a static variable inside this function, static integer x, initially 0. And before calling itself, let us do x++ and return plus x. This is what I have explained you on the board. So the same thing I have written here. And when we have traced that function, the result was 25. Let us run and check what the result will be. Here after %d, here inside printf, after %d, I will give /n. So it gives a new line after printing the result. Let us run the program. See, the result is 25. Let us debug this program and see. So for debugging, I will take a breakpoint. Then I run the program. It will stop here at the breakpoint. Inside debugger window, you can see that just it's in the main function, and it has stopped at this function call. I will continue running. Next line. Now the function is called. You can check the value of n is 5 and x is right now 0. The next statement, it will do x++, then it will call itself. So now you can see that the value of x has become 1, and this is the second call. Here in the debugging window also you can see that there are two functions calls, but the value of x is 1. Let us continue. Now x++ value of x becomes 2. You can check it here. See, x value is 2. Then again it will call itself. Again it will call itself. Again it will call itself. So right now n value is 1 and the x became 4. And then next statement, x becomes 5. Now n value is 0 and x is 5. Now for 0 it will not execute, it will not enter inside if block, and it will return 0. Yeah, return 0. So it goes back to the previous call. Now in the previous call the value of n was 1. Now it's about to add this value. See, the value of x is 5. 5 is added with this one. Because x is static, there is only one copy of variable x. And here inside this wash you can see that x is 5 and n is 1 at the bottom. If I continue, it will go back to the previous call where the value of n was 2 and x is still 5. Then continue, it will go back to the previous call where the n value is 3 and x is 5. Because when it has reached till n equal to 0, by that time x became 5 and x remained 5 while returning time also, because there is only one copy of variable x. If I finish this, then here in the next line the value is 25. Yes, we got the same result. So we have seen how the function is working. Now I will modify this function. I will remove the breakpoint. Let us modify this, and instead of static variable I will remove this and I will make it as a global variable. Out x assign 0. So this is a global variable outside all the functions, so it's accessible to all the functions. Now I will run this. Answer is 25. So it's working same. Now I'll show you one thing. See, here I have called the function for 5 one time and I have displayed its result. I will do it again. So again I will call the function for value 5 and again print the result. So if you check this variable x, that will become 5 in the first call. Then the second call it will become 10. Then the second call it will start from the same value 5. So let us see, when I call the same function for 2 times, then what will be the result at 2 times? It will not be 25 at both the times. See, first time it is 25 and the second time it is 50. The reason is, when the first call is made, it has made the value x as 5. Then the second call is again trying to increment x for 5 times. Here x plus plus, then x will become 10. And 5 times 10 is added, so it is 50. So that's all. We have seen the effect of static variables and global variables. Sometimes they are very useful. Some type of problems we cannot write them in the form of some functions, we cannot write them recursive. We may have to use static variables, so we will see them when we come across such topics. Now we'll start the next topic, that is types of recursions. So here are the list of types of recursions. I'll be discussing each of them one by one by taking some examples. See, the tail recursion is the first one, then head recursion, tree recursion, indirect recursion, and nested recursion. So we'll look at them one by one. Let us start with tail recursion. Yeah, here is the first recursion, that is tail recursion. We have already seen this type of recursion. This function already I have explained in the previous video. Now it is a tail recursion. So what does it mean by tail recursion? If a recursive function is calling itself, and that recursive call, this is called as recursive call, and that call is the last statement in a function, then it is called as tail recursion. After that call, there is nothing. It is not performing anything. So it is called as tail recursion. For example, this is fun and taking some parameter n, and if n is greater than 0, the similar one I am writing, and there are some statements inside, then the last thing is it is calling itself by a reduced value of n. See, what all it has to do, it is performing first then it is calling itself. So in this example, I have just written printf, but there may be a lot of things a function may be doing. All those things it has finished, then it is making a call to itself. So if it's a last statement, then it is called as tail recursion. So this means that all these operations will be performed at calling time only, and the function will not be performing any operation at returning time. Everything is performed at calling time only. So that's why it is tail recursion. Now suppose there is something written here, plus n, means along with the function call some operation is done. Then if this is the case, then when this operation will be performed, this will be performed at return time, because unless the result of this function is known, addition cannot be done. The value of the function is added with n, so this addition can be performed only at returning time. So in this function there is something remaining that has to be performed at returning time, so it cannot be a tail recursion. Tail recursion means at returning time it doesn't have to perform anything at all. So this is a perfect example of tail recursion, or else if I remove any processing here, then it is a tail recursion. Now next I will compare tail recursion with loops. Now comparison of tail recursion with a loop. So first and the foremost thing I have to tell you is that every recursive function can be written as a loop, or vice versa. Every loop can also be converted in the form of a recursion. But now let us compare tail recursion with loop. See, this is a tail recursion. Already you know the answer in the previous video. Already I have traced this one and shown the output. If we call this function by passing 3, so it will print 3, 2, 1. And it will stop when the value of n becomes 0. So it will print the values 3, 2, 1. And it will print in calling phase. Now same function, I want to write it using loop instead of recursion. So I will write on the function here void fun, which takes parameter n, and the first thing is n greater than 0. I will write n greater than 0, but instead of if, I will write it as while. Then inside this printf statement, this is printf percentile d and some space n. Then calling function again itself by reduced value of n. So let us do n minus minus. That's it. So if I call this function by passing value 3, then 3 will be passed here, then it will first print 3, then it will make 2, and again repeat. So print 2, then repeat, print 1, then repeat, it is 0, so it will stop. So this will work same as that recursion. As it is, I have converted, just instead of conditional statement, I made it as a loop. Instead of conditional statement, I made it as a loop, and instead of function call with reduced value of n, decreased value of n, I have just written n minus minus. So the function is same as that one. Output is same, and the structure also, if you see, it looks more similar. That's what. So the point that I have to tell here is that tail recursions can be easily converted in the form of a loop. Now let us decide who is efficient. In terms of time, if you analyze, this is printing 3 values and this will also print 3 values. So the amount of time spent is same. Whatever the value of n is given, if it is 3, then it is 3. If it is 5, then it is 5. So it means the time taken by both of them is order of n. So time is same. So the time taken by both of them is same. So the time is order of n. But let us analyze the space. This is a recursive function. It internally utilizes stack. So for the value of 3, it will create a total 4 activation records in a stack. This already we have done the analysis. So for n, the space taken by this one is order of n. But what about this one? This is a loop function. So how many activation records will be created? Only one. It is not calling itself again. So the space complexity for this one is order of 1. So it will just create only one activation record. So that is constant. So we say it is 1, order of 1. That is constant. So there it is order of n, and here it is order of 1. So the conclusion is If you have to write a tail recursion, then better you convert it into a loop that is more efficient in terms of space. But this will not be true for every type of recursion or loop. In case of tail recursion, loop is efficient. And even I have to tell one more point, that some compilers under code optimization inside compiler, they will check if you have written any function which is a tail recursion, then they will try to convert it in the form of a loop. It means they will try to reduce the space consumption and they will utilize only order of one space. So your function will be converted into object code just like a loop where the space is reduced. So that's all about tail recursion. Now next we will see head recursion. Now let us see head recursion. See, this is a structure for head recursion. If there is a function that is calling itself, so it's a recursive function, then the first statement inside the function is recursive call. It is calling itself here. Then what all the processing it has to do, it is doing it afterwards, after the recursive call. So there is no statement, no operation before the function call. See, if there is something here, then it is not a head recursion, right? If something is there before the function call, just it is a recursion. We don't have to give any special name for that one. So there is nothing before that one, then we can say this is a head recursion. So what do you mean by head recursion? It means the function doesn't have to process or perform any operation at the time of calling. It has to do everything only at the time of returning. So all the processing is done at returning time. Then such functions are head recursion. So the example of this type of recursion already we have seen in the previous video. This was the simple example. So you can see that the function is first calling itself, then the second statement it is printing. So the printing will be done at returning time. So the function doesn't do anything at calling time. So such recursions are head recursion. Next, we will compare head recursion versus loop. Can we convert them into loop? Let us discuss this. I will try to write the same function using loop. So let me write here void function fun. Now instead of conditional statement, I have to write a loop that I already have shown you. So if n greater than 0. Now here first it has to make a recursive call, then it is printing. So if you remember the output of this one, the output of this function was 1, 2, 3, as it's going to print at returning time. So if you remember the answer in the previous video, or else you can check back, the result of this type of function is 1, 2, 3 because it is printing at returning time. Now as it is, I have tried to write the function with a loop. Now I want the output to be 1, 2, 3. So if I use printf here, printf %d n, then if I am passing function fun with value 3, then first value of n will be 3. So 3 is greater than 0, yes. So it will print what? 3. It will not print 1. First value that will be printed will be 3. It is not 1. Then if I have to repeat, then just like this one, instead of that if I write n minus minus, then it doesn't work same as that one. So you cannot easily convert it. So you have to write it in some other way to get the same output. But as it is, looking at the function, if you try to convert, it's not easy. We can write some function which prints 1, 2, 3 using loop, but looking at this function, we cannot directly create it. So it means I have to write it in a different way. So let me write it. Suppose I have to take some variable I, and that is value 1. Then I should say I is less than equal to n. Then here I should say I plus plus, and I should make this I plus plus after printf. So let us try to run and see this one. If I pass the value as a 3, that is n is a 3. So I is 1, 1 is less than 3, so it will print I, that is 1. So output is 1. Then I becomes 2, so 2 is less than 3, so it will print 2, so result is 2. Then I plus plus, I becomes 3, so 3 is less than or equal to 3, so I is 3, so it will print 3. Then I plus plus, I becomes 4, 4 is not less than or equal to 3, so it will not enter in, and it will finish the loop and it will come out. So the output is 1, 2, 3. So that's it. You can see that that function cannot be as it is converted. So head recursions, or if a recursive function has to do something at returning time, it cannot be easily converted in the form of a loop, but it can be converted. It doesn't look as it is. So that's all about head and tail recursion. In the next video, we will see tree recursions. In this video, we'll learn about tree recursion. So first of all, I will compare what is linear recursion and tree recursion. Let us see. See, a linear recursion, a function that is a recursive function, if it is calling itself only one time, you can see that the function is calling itself only one time, then it is a linear recursion. So already we have seen in the previous video that the functions which are calling just one time, and we have seen head recursion and tail recursion, but in this example it is having something to process before the call as well as after the call, so it is just a recursive function, right? We cannot name it as head or tail recursion. And this code is not a C or C++ code. I have just written a pseudo code here, so it's not a complete function like now integer, everything is not there. So don't try to read it as C language code. Just I am showing you structure. Then here, tree recursion. So what is tree recursion? If a function that is recursive function is calling itself more than one time. So here you can see it is calling itself first time, and here it is calling itself second time. So if a recursive function is calling itself more than one time, then it is tree recursion. So in my example, I have shown it as 2 times. So it may be more than 2 times also. So that we call it as tree recursion. So here I have one example of tree recursion which is similar to the previous examples, only the difference it is calling itself more than one time. So I will trace this one and show you how it will work and what will be the output, and also I will show you how the stack is created in this one. Let us look at the tracing of this function. The function is called by passing value 3. I have taken a piece of stack. I'm not taking complete memory, entire memory, just I am showing you stack, how it is used by this recursive function, which is a tree recursion. Let us trace. First it is called by passing function with value 3. So the first call is fun of 3. For this function, an activation record is created and the value of n will be 3. So this is the first record created. Then what are the steps it has to perform? First print the value, then make 2 calls. So it will print the value, then it will make 2 calls. Let us print the value. See, it will print the value 3 and make first function call fun for n-1, that is 2. And second call it has to make, that it will be doing once this call has finished. So let us first finish first call. So for this call, and again activation record is created where the value of n will be 2. Now for this call, let us see what happens. N, that is 2, is greater than 0. Yes, 2 is greater than 0. Print and then make 2 calls. So let us do it. Print 2 and make 1 call with n-1, that is n-1. So 2 minus 1, 1. Then second call it will make after finishing this one. So far we have 2 values printed. So I'll also be writing the output here. So the output of the function so far is 3 and 2. Now let us continue with this call. This call, again an activation record is created and the value of n will be 1. Now for the value of n is 1, 1 is greater than 0, yes it is greater than 0, then it will perform 3 steps. First print 1, then make 2 calls. So first it will print the value that is 1, then it will make first call with reduced value of n. So this is 1, so it will be 0. And second call it will make afterwards. So for this call, again a fresh call is made from here. So a new activation record is created where the value of n will be 0. Now this time fun of 0, this is 0, 0 greater than 0, no. So it will not enter inside and it will not perform these steps. So the function call terminates. Now the function calls terminates. This activation record is deleted from the stack. So before deletion, if you count 1, 2, 3, 4, 4 activation records. How many calls? 1, 2, 3, 4. 4 calls. So 4 activation records are there. So this is deleted. Now once it is deleted, it will go back to the previous call. It means this has finished. It will go back to the previous call. In previous call, for performing 3 steps, first was completed, second is also completed just now, third one has to be performed. So it will make a call here for n-1. Next call, n-1. So n-1, 1 minus 1 is again 0. So again it will make a call with value of n as 0. So again the activation record is created. Actually this was gone. So new activation record is again created. So I have erased this one. So let us assume again it is created here. So now again the size of the stack is 4. Next, for fun of 0, this is 0. 0 is not greater than 0. So it's not going to enter inside. Function ends. So this activation record is deleted and this function terminates. So now you can see that for fun of 1, all 3 steps are completed. Printing, calling itself 2 times with reduced value of n. That is 1 is printed and 0, 0 is called and they have finished. And in the output we also have 1. Now this call is completed. All 3 steps are over. So it will go back to the previous call. So go back to the previous call means this call has finished, means this activation record is deleted. So right now there are only 2 activation records in the stack. One is for value of n as 3 and value of n as 2. Now it is back on this call where n is 2. And in that, out of 3 steps, it has already performed first step, printing of 2 and call. Then the next again it has to make a call, that is n-1. So now it will make a call for fun of n-1. So again fun of n-1, that is 2 minus 1, that is 1. Now again a fresh call. So new activation record is created. Now for this it is 1, so it will print 1. Now all these things that happens will be similar to this one. So it means it will print 1 and then it will call itself for, now I will not write complete name fun, I am just using f because of lack of space. F of 0, so this activation record is created again. Then this ends, so this is deleted, then goes back, again call for 0. So again an activation record is created for 0 and this ends and this is deleted. Now control goes back to this is finished, goes back to this, all 3 steps are finished, then goes back to fun of 3. In this it has to perform one more step, that is fun of, this was 2, so this is also 2. So 3 minus 1, 3 minus 1. So again 2 calls are made. So already this portion we have seen it completely. Same thing happens here also. Here also same thing happens. Now this I have taken enough space for explaining this one. Now this I have to write it in small size, but it will happen as it is what has happened here. So let me finish it quickly. So the first thing happened is value 2 is printed. 2 is printed. And here activation record is created. Then call for fun of 1. New activation record for this was gone, sorry. So 1 is created. Then for this, value 1 is printed. Value 1 is printed. Then call for fun of 0 and this ends. Activation record one more is created with value 0 and this ends. And again a call for fun of 0. Again and 0 and this also ends. This also goes back. Here fun of 1. For this 1 is printed. So output is 1. Then call for fun of 0, call for fun of 0, right? So again 2 more activation records, then that also finish, this also finish, and finally 3 also finish. So this is the output that we get. So I have simultaneously shown you how the activation record works. So you can see that maximum size of the stack was how much? 1, 2, 3, 4. Maximum was 4. 1, 2, 3, 4. And total how many activation records are created, as many calls are there, right? I did not draw all, just I have given the idea. I did not draw each and every call here. So if I count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So total 15 calls are there. So 15 times activation records are created and deleted. Now I will remove this stack and redraw this tree once again, and we will analyze more on the tree. I have redrawn the tree once again. Let us analyze the tree, so by which we can analyze the working of this recursive function. So here is a tree. Now first of all, let me label the calls in which order they are called. See, the first function call is this one, 1. Then second call. This will be done once this has finished. It has to finish. So under that there are 3 things again. So second call, printing is done. Then third call. Then this one will be done once this has finished. So under this, printing. Then this call, fourth call. Now this is fun with value 0. This will terminate. Then it will go to this call. So this is fifth one, fifth call. Then as this has finished, it will go back and then it will make this call. So this is sixth call. Then under this, 7th and 8th. Now these are also finished. So under this, if you see, all the calls are completed. Now it will go to this one. So this is the 9th call. So that is the 9th call. 9th activation record to be created in the stack. Now height is how much? 1, 2. So only 2 will be there in the stack. But the count, if you take this, the 9th one. So this is 9th call. Then under this, printing is done and this call is made. So this is the 10th call. And then printing is done and this is made, 11th call. And this will finish now because value of n is 0. Then this call, 12th call. So this is also finished because the value is 0. So this will also complete. All 3 steps are completed under this one, 12th call. Then go back for this one, right side. 13th call, then 14th call and 15th call. So that's what already I have counted them. So total 15 calls are made in this particular function when we pass the value as a 3. So I have shown you the order in which the calls are made. This is very important for you to visualize or trace how these type of functions work, which are calling themselves more than one time. Now we will analyze the time complexity. So time complexity depends on the number of calls. Yes, in each call it is printing, except in the calls where the value is 0. So otherwise it is printing almost for every call. Then, now let us see how many calls are made if the value is 3. So for n, how many calls will be made? With that we can decide the time complexity of this one. So let us analyze this one. So if I count the number of calls level wise, then in this level just one call is made, and in this level if I see 2 calls are made, 2, and in this level 1, 2, 3, 4 calls are made, 4, and this level 1, 2, 3, 4, 5, 6, 7, 8 calls are made. So it means when I have passed the value as a 3, Then in the first level, 1 call, next level 2 call, next level 4, then next 8. For 3, there are 4 levels. And if the value of n that I am passing here, this value n, if it is 4, then there will be 5 levels. It means the tree will be more bigger than this one. Then how many calls it may be having? So let us analyze this one. So for any value of n, how many calls it will be? So let us sum up all these. So I will take the sum of all those. 1 plus 2 plus 4 plus 8. This is total 15. Yes, we know this. Count all of them, that is 15, or you have add all these, you get 15. So this is nothing but 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3. So this is nothing but sum of the terms of, that is summation of terms of series, that is GP series, that is sum of geometric progression terms. What is all that GP series and all, we will learn some other time, but right now I'll just write on the formula. So this will be nothing but 2 power, highest term is 3, so this is 3 plus 1 minus 1. So it means if I have 2 power 0 plus 2 power 1 plus 2 power 2 goes on to, if this is n, then this will go till 2 power n. Then how much that is? This is 2 power n plus 1 minus 1. So that many calls it will make. So what is that equal to? So this is order of 2 power n. So total 2 power n calls are made. So if I substitute the value of 3 here, so 2 power 3 plus 1, 4. 2 power 4 minus 1, that is 16 minus 1 is 15. So for any value of n, the number of calls will be order of 2 power n. So that's all. We have seen what is tree recursion, and we have taken one example, and we have seen how the tracing tree is generated and how the calls are made, how the stack is used, and what is the time complexity. So for this example function, it was 2 power n. So it depends on the function what time complexity you may be getting. It's not that every tree recursion will have 2 power n. For this function, it is 2 power n. So the time is order of 2 power n. Then what is the space? What is the space complexity? So it depends on what is the maximum height of the stack, because total activation records depends on number of calls, but how much space it was occupying inside the stack. So you have observed that same space was reused inside the stack. One activation record was gone and the same place another activation record was created. So we don't require much space, just like 2 power n, but we require the space equal to the height of a tree that we got here. So 1, 2, 3, 4. If it is 3, 4 is the space. So if it is n, n plus 1 will be the space. So it is order of n. Space complexity is order of n. So maximum stack size that we need is n. That will be sufficient. So that's all about tree recursion. Let us look at tree recursion. For that I will create a new project. Project type is command line tool. Project name I will give it as tree recursion. Next, create the project. Your project is ready, and here is the main function. Here I will write down a function for tree recursion, the one we have already discussed. Function fun, which takes parameter n. If n is greater than 0, then printf the value of n. Next, it will call itself by passing n minus 1 for 2 times. Now this function I will call it from main. Function fun by passing value 3. Let us run the program. See, the output is 3211. 2 1 1. Here is the output 3 2 1 1 2 1 1. So the same output we got. Now let us debug this program and check how these functions are called and how this output is generated. So I'll put a breakpoint here and I will run the program. So debugger stops here at the breakpoint and at the beginning point of the function call. Inside debug navigator we can see just main function. Now here we will observe how the function calls are created and destroyed. You can better watch in this watch window how these function calls are created and how the value of n are changing. So let me continue. The first function call, you can see here that n is 3. Inside watch n is 3. Printf, it will print 3, then it will call itself for 2. Now this time n is 2 and there are two function calls here in the debug navigation. Printf2, then call itself for function 1, then printf1, then call itself for 0. This time it will not execute. So total 4 calls. This is for 3, 2, 1 and 0. From the bottom if we check, don't go on these numbers. These are actually the ordering, that is 0th call, first call, second call, so on. This is not the values of n. Now this function ends and it will go back to previous call where the value of n was 1. Then it will make a second call. Now you can see that it is on the second line. The second line is highlighted with green color. It's going to execute the second call. Now the value of n is 1. So again 1 minus 1 0. Yes, the function call is for 0. Here you can see in the watch window value is 0. And again the function calls are 4. This function will not enter into if, it will come out. Then it will go back to function call for 1. Then back on 2. Now for 2, first call has finished. Now it is going to make second call for 1. N value is 2. Now for 1, 1 is printed once again. So here we got the output. Then for 0, again 0, 2 calls are over. Now back to 2 and back to 3. Now for 3, when the n value was 3, this first call has finished. Now the second call will be done. So it will be 3 minus 1, 2. So same thing, just how we got a 2 1 1, same way we get a 2 1 1. Now you can see here inside the debug navigation, that is main function, and only one function is there with the value of n as 3. Now again it will expand, it will be ascending. Print 2, call for 1, print 1, call for 0. Now again you can see that here 4 function calls are there above main. This ends and 0 also ends. 1 is printed, 0 is called, 0 terminates, 2 terminates and 3 terminates. It's returned back to main function. So the things to observe here are how many activation records are created inside the stack. If you count total calls are 15, but at most at a time maximum 4 calls were there. So that's all about this tree recursion. Now let us look at indirect recursion. In indirect recursion, there may be more than one function and they are calling one another in a circular fashion. So that if the first function calls second one and the second call third one and the third one again call back first function, then it becomes a cycle, so it becomes a recursion. Like suppose there is a function A and the function A is calling function B and the function B is calling function C and C is calling A again. So instead of a function calling itself, here function calling another function and is calling another function and that C is calling A, so it becoming a cycle, so it becomes a recursion. So here I have a skeleton for showing you indirect recursion. Here is function A is having some condition, and if condition is satisfied, it is calling function B. And the function B, there is some condition, if it is satisfied, it is calling function A. So from here it is calling B, and then B is calling A, so it becomes our indirect recursion. Here B is called with reduced value of n, and again A is called with some more reduced values of n. So they are calling each other. At one point they may stop if the condition fails. If any one function stops, then it will return back to the first starting call. To explain how this works, I have set of functions as an example here. These are in indirect recursion. So let me trace this with an example and show you. Let us trace this example. So first of all, I will read it out. See, this is a function A. I'm taking parameter n. If n is greater than 0, then it is printing and then calling function B by passing n minus 1. This function B, if n is greater than 1, then it is printing and calling function A by passing n by 2. So I'll start this by calling function A first. Let us say function A is called for value 20. Let us trace this one. Function A is taking 20 as parameter, 20 is greater than 0. Then it has to perform two things, that are print the value and call function B by passing n minus 1. So function A will be calling B by passing n minus 1. So the first thing, it will print 20 and it will call function B by passing 19. Now what function B does? Function B, if n is greater than 1, then it will print and call function A by passing n by 2. So two steps are there. First print and then call function A by half of n. So this is function B, so it will print 19 and it will call function A by passing 19 by 2, 9. Now again control goes back to function A. Function A takes the argument, and we know well that it's printing and calling B. So prints 9 and call B by passing n minus 1, that is 9 minus 1, that is 8. Now it is back on function B. Function B, print and call A by half of this one. So print 8 and call fun of A by passing half of 8, that is n by 2 of 8. So it is 4. Now again function A prints and call B, prints 4 and call B by passing 4 minus 1, that is 3. Now function B, n is greater than 1, yes 3 is greater than 1, print and call function A. So 3 is printed and call function A by passing 1, that is 3 by 2. That is integer division. We are doing integer division here. Now A, it will print 1 and call B, function B, by passing 0. Now function B, when n is greater than 0, it works, otherwise it stops because n is 0 now, so it will not enter inside, it will terminate. Once the function terminates, it goes back to function A, then B, then A, then B, then B, A, then B, then A. So it goes back and reaches the starting point and the function calls ends. The output will be 20, 19, 9, 8, 4, 3 and 1. So that's all about indirect recursion. I have just taken a sample program to demonstrate how indirect recursion works and what does it mean. Now in this video we will write a program for indirect recursion that we have already discussed in previous video. So we will have a demonstration of that indirect recursion. So for indirect recursion I will create a project, but this time I'll give the project name as recursion. All other demos I will do in the same project. I will not be creating project every time. I will just delete and write down the fresh code. But the project will remain same, so the name I have given as recursion. Already you have seen how to create a project, so I will utilize the same project for all other demos. Create a project for recursion. Here is the main function. I'll remove this. So here I will write on two functions. Function A, which takes parameter n. If n is greater than 0, printf n and call function b for value n minus 1. Next I should write on function b. Function b, it takes parameter n. If n is greater than 1, then printf value of n and then call function a by passing n by 2. Now here I am getting an error saying that this function b is not defined before it is used. It is used here in function a. So if you read the code from here line by line, then first we are coming across a call to function b, then later on we are having a definition of function b. So this function b should be defined before it is used. So here I will write on the prototype of function b. So error is gone. So before using a function, it must be either declared or defined. So definition we have written here. So that's why we have to write declaration so that we can call it at this place. Now these functions we have called them by passing value 20. Let us run the program and see what the output we get. If you remember the output is 20, 19, 9, 8, 4, 3 and 1. So we have already seen it's working. I have explained you everything. So just for the demonstration, I have written the program. So I got the result. So that's all with the indirect recursion. Let us look at nested recursion. In a nested recursion, a recursive function will pass parameter as a recursive call. See, here is a recursive function and it is calling itself, so it is recursive. It is calling itself here. But what the parameter is? Parameter itself is a recursive call. Means unless the result of this recursive call is obtained, this call cannot be made. So a recursive call is taking a recursive call as a parameter. So this is recursion inside recursion. So it is called as nested recursion. So for as an example, I have one function here. I will trace that function and show you. Here is a nested recursive function example. Let me read it out first. A function which is taking parameter n, and if n is greater than 100, then directly it is returning some value. If not, then it is making a nested recursive call. So function call is again taking a parameter as function call with some increased value of n. So for tracing this one, I will take the value that is 95 and let us try this 95 on this one. So I will trace this function for this value. So let us start. First function call fun of 95. 95 is greater than 100? No. Then it will enter into else part. So in else, it will call itself again by passing fun and again fun of 95 plus 11, that is 106. So first of all, I should know the result of this one. Then I can use that value as a parameter for this function call. Let me evaluate this one first. See, fun of this is 106. So fun of 106. Let us check this call. Fun of 106, 106 is greater than 100, so it returns 106 minus 10, that is 96. So the result of this function is 96. So this 96 is the result of this function call, so this has to be placed here. So it becomes function of 96. So actually we started with 95, then the next call is nothing but 96. Now for 96 is not greater than 100, so it enters into this else part. Then it will make a function call with again nested function call with what is the value of n plus 11. So it is 96, 96 plus 11 is 107. So directly I am writing the value. So I should know what is the result of this fun of 107. So let us find out fun of 107 here. Fun of 107 When this is fast, n is 107, so 107 is greater than 100, so it returns 107 minus 10, so this becomes 97. So this is the result of this function call. So actually this function becomes now fun of 97. Now let us solve this fun of 97. 97 is not greater than 100, so it will enter into the else part and it will make the function calls, that is fun of n plus 11, that is 97 plus 11, so this becomes 108. Now as we have already seen these two calls, see this was 106, so it becomes 96, 107 became 97, so 108 will become 98. Instead of tracing it, I will directly write down this result, so this is 98. So fun of 108 is 98. So this function call becomes actually fun of 98. Now fun of 98, 98 is not greater than 100, so it enters into the else part. Then it becomes fun of 98 plus 11. So this becomes 109. And this function 1 of 9, this becomes fun of 109 becomes 99. So this is fun of 99. Fun of 99 is not greater than 100, so it will go into the else part. So fun of 99 plus 11, so this becomes 110. Now what is the result of 110? Fun of 110 will be 100. Here it enters into the if part and returns minus 10, so this is 100. So this call becomes fun of 100. Now fun of 100 is not greater than 100, so it will enter into this part. So I have to continue here. I will continue here. So this becomes fun of 100 plus 11. So this is 111. Now fun of 111, this is greater than 100, so this is 111 minus 10, so this becomes 101. So this function call, finally it becomes fun of 101. Fun of 101, again it is greater than 100, so this will be 101 minus 10, so this becomes 91. Now this time it will not enter into the else part and it will return 91. It goes back to this call and goes back to this one and this one and this one and this one. Finally the result of this one is 91. So that's how I have taken one simple example to show nested recursion. Usually nested recursion, if you want to trace them, they expand like anything. It will become a big tree. So here you have observed that for every nested call, first of all, we should know the result of this one, and that result is utilized with this function call. Like here I have written fun of 96. Then again, there's a nested call. Then I should know the result of this one, that is 97, and I use that 97 here with fun of 97. So every time you have to find out the result of nested or inner call, then you can make a outer call. You can find out the result of outer call. So that's all with nested recursion. We will see more examples on recursions in coming videos. In this video, we'll look at the demonstration for nested recursion. The project is ready. I am using the same project, and here I will write on the code for nested recursion. I will write on the function that we have already seen. Function takes parameter as n, and if n is greater than 100, it will return n minus 10. Otherwise, function will return function of n plus 11. So this is a nested call. Then from the main function, I will take some temporary variable r. Then in r, I will assign the result of the function call by passing 95, the value that we have seen. Then here I will print the result of R. New line R. That's it. It's a simple function. The same result we get, we know the result, that if 95 is passed, what is the output? So let us run the program and see the result. 91 is the result. Yes, already we have traced this program and we have seen it. If I pass the value 99, let us see what will be the result. Still 91. If I pass the result as 100, then let us see what is the result. Still 91. If I pass 200, 190. See, if n is greater than 0, it is just returning n minus 10. So what is the value of n is minus 10, otherwise these calls are made. If I pass the value 30, then let us see what is the result. So again answer is 91. So this 30, the value 30 will grow up to the value 101, and then from 101, when 10 is subtracted, it gives 91. So for any value, this function is going to return value 91. So you can debug this function and check. So I am not debugging now. Already I have shown you how to debug the program. So whichever editor you are using, you can try debugger. That will help you clearly understand the flow or the working of program. So that's all in this video. Now let us look at an example recursive function for finding sum of first n natural number. So first of all, I'll explain you what does it mean by sum of first n natural number. Then I will devise a recursive function. Then we will write a recursive procedure, that is function, using C or C++ language. Let us understand what does it mean by sum of first n natural numbers. So if I take some natural numbers like 1, 2, 3, 4, 5, 6, 7. Suppose I want to take up to 7, then I want the sum of all these. Summation of first n natural number. So how many natural number? First 7. So first 7 means 1 to 7. Now same way, if I say first n natural numbers, then it is 1 plus 2 plus 3 plus 4 plus goes on to last term is n. N can be anything. Like in this previous example, it was 7. It can be anything. Now for this summation, let us write a recursive definition. So for recursive definition, I will say sum of n terms is 1 plus 2 plus 3 plus 4 plus goes on to. Now before nth term, there will be n minus 1, then n. So I have included one more second last term. I am showing it. Now, if I take the summation till here, this is nothing but sum of n terms is sum of, this is n minus 1 terms. See, n terms means 1 to n, then n minus term will be from 1 to n minus 1. Then 1 to n minus 1 will be from here to here, that is till this point, Then what more is remaining? Plus n. Then if I add n to that, it gives me up to n. So this became a recursive definition. Now this I can write it like this. Sum of n terms can be defined as sum of n minus 1 plus n if n is greater than 0. If n is equals to 0, then it's not a natural number. Natural number starts from 1 onward. So n is 0. So let us say answer is 0. See, remember, whenever you define any recurrence relation or recursive function, then you must have two type of statements. One is for the large value of n, what is the formula? Then for the small value of n, what is the answer? So usually for small value, we give a direct answer. So if n is equals to 0, there is no formula, direct value is there. So based on the same thing, I can write a recursive function in C or C++. Let us say int sum, which takes integer parameter n, and if n is equals to 0, return 0, otherwise return sum of n minus 1 plus n. So here what I want to explain you here is, if you have a recursive definition of any problem, then directly you can convert into a recursive function in any programming language which supports recursion. So in C, C++, you have recursion, so you can directly convert this one. See, if sum of n, and if n is equals to 0, return 0. If n is equals to 0, return 0. Otherwise, if n is greater than 0, then return sum of n minus 1 plus n. So sum of n minus 1 plus n. So that's it. That is a recursive function for finding sum of first and natural number. Now finally, I have one more thing to show you, that for finding the sum of first and natural number, there is a direct formula, that is n into n plus 1 by 2. So this is the formula. So it means I don't have to write a function for that one. Function will consume time, and it's a recursive function, and it will take time for making number of calls. Instead of that, I can simply use a formula and write a program. So usually we write just a formula whenever we have to find out sum of first and natural number instead of writing a function. But for experiencing or learning recursive functions, I have taken this example. Even the same function, we can write it using iteration, that is using loop. Recursion will be costly because it uses stack internally. So I will write down two more versions of the same function. Instead of recursion, I will use loop, and also I will directly use the formula and show you. So I will remove this definition, then I will write down two more functions. Here I have a function for sum which is directly using the formula. If you pass the value n, then it will take the formula. Using the formula, it evaluates n into n plus 1 by 2 and returns the result. So this is the simplest function, and it will take very less time. It is just constant time because just it has to evaluate a simple expression. So I can say that the time taken by this function will be constant. Few number of operations like 1 operation, 2 operation, and 3 operations. So total it may be performing 3 operations, that is constant. So this is the fastest method. This is using formula. Now here I have a function for finding the sum of first and natural number using loop. Now this function, it takes the value of n and it will start I from 1 to n. So I will start the values from 1 to n. Initially s is 0, so this I value from 1 to n will be keep on added to that s. So first time 1 is added, the next time I becomes 2 and 2 is added, then 3 is added, then 4, up to n all numbers are added, and this is returned. So this is using loop. I have written the function. If I find the time complexity of this function, so one of the major important statement is this one, and this statement is repeating for n times as I is taking the values from 1 to n. So this will be repeated for n times. This is statement one time only, and this is statement one time. And if I consider for loop, mostly it is written as n plus 1 time. So the main statement is this one. So this is executing for n times. So I should say that the time taken by this algorithm is order of n. Time taken is order of n. I have found out the frequency of execution of each statement, and this the main statement is this one where the addition is done, and that's going to execute for n time. So our focus is on that statement, this order of n time. And how much memory it takes? Just 3 variables are there, that is I, s and n, that is passed as parameter. Only 3 variables are there. But what about recursive function? A recursive function internally uses stack. Whatever the value of n we pass to that, it will make those many calls and it will create those many activation records. So it's having just one variable n, so that n variable will be created many times, as many times, depend on the value that you are passing. So it takes more space, but the time will be order of n only. So let me trace this function and show you for the value 5. If I call this function sum for value 5, then what it will do? If I pass 5 is not 0, then it will call sum of n minus 1 plus n. So it will call itself for sum of 4, and the value of n is what? 5, that is added. So it's making one more call. Then in this call, again the same thing, it's not 0, so it will make a call for sum of 3 and then also add 4. Then it will make a call for sum of 2 and also add 3. Then sum of 1 and also add 2. Then sum of 0 and also add 1. Now finally, sum of 0, as it is 0, it returns 0. So this is 0. So 0 plus 1 is 1. And this is written here. So this is 1 plus 2, that is 3. So 3 is written here. So this is 3 plus 3, that is 6. 6 is written here. So 6 plus 4 is 10. 10 is written here. So 10 plus 5 is 15. 15 is written here. So the result is 15. So while returning, the addition is done, and you can see that how many calls it has made. For 5, it has made total 6 calls. So the size of the stack is 6, and the variable n is created for 6 times. So memory is more. But how much time it is taking? There are total 6 calls. So for value of 5, there are 6 calls. So for value of n, there will be n plus 1 call. So it is order of n. So the time taken by this function is order of n. But space is also 6 times for the value of 5. So the space is also n plus 1. So space is also n plus 1 here. This is time. So there, recursion is costly, but it was easy for converting a mathematical definition, that is recursive definition, into a function. That's how recursions are easy to write compared to loops. For loop, we have to devise some logic, work on the problem, understand the problem, devise some logic. Then it may work faster compared to recursion, and it takes less space compared to recursion. So mostly in our applications, in our program, we write loops only instead of using recursions. But actually, the problems are solved using recursions in mathematics. So I have taken a very simple example, and I have shown you how we can define a recursive function for finding sum of first and natural numbers. Now in the coming videos, we'll see more examples of recursion. In this video, I will show you a recursive function for finding sum, and also I will write a iterative version of sum of first and natural numbers. So let us write the program that we have discussed in the previous video. I will write a function for finding sum of first and natural number using recursion. Int sum, which takes parameter n and returns an integer. If n value is 0, return 0, otherwise return sum of n minus 1 plus n. So this is the function that we have already seen. So directly I have written that function. Now here inside the main function, let us take a variable r for getting the result of that function sum, and I will pass the value 5. Then I will print this result. That's it. A function is ready, a recursive function. A function is very small because it is recursively defined. I will run the program and show you. The result, we know it should be 15. So yes, the result we got it as 15. You can debug this function and check it. Already I have shown you how to debug it. So you can see how many function calls are made and how the values of n are changing. Now we'll write a function isum, that is for iterative sum of first and natural numbers. So here I will take a temporary variable s and also I. S is initialized to 0, in which I will store the sum of all the numbers. I starts from 1, I is less than or equal to n. So this is a for loop, I plus plus, sum assign sum plus I every time. So I will be taking the values 1 through n, and all those values are added to sum. Then finally return sum, that is s, variable s. Inside the main function, instead of recursive sum, I will call iterative sum, isum. Then let us see. Now I will run the program. We should get the output 15. Yes, again we got 15. So the result is same whether a function is recursive or iterative. Let us debug this function and check how the iterative function is working, how this loop is working. I will put a breakpoint here on the function call inside main. Then I will run the program. So it has stopped at this function call. I will continue execution. It will enter into isum. Now it has entered into isum. Now you have to look at this window where the value of n is 5 and s is 0 in this inside this function. So we have variables n s and I. So you have to look at the values of these three variables here inside the window. See how they are changing in a loop. Now I is also 0. So it is upon the for loop now. It is upon the for loop. Now I am continuing. I is 0. Then this I will be added to s. Here I will be added to s. So s also became 1. So inside the watch you can see that s has become 1. Then continue. I became 2. Just keep watching here. Then 2 is added to s, so s became 3. Then I became 3. 3 is added, so s becomes 6. Then I becomes 4. 4 is added, so s becomes 10. Then I becomes 5. 5 is added to s. Then s becomes 15. And I becomes 6, so it terminates for loop. Then it will return the result. So that result is in R now. Now R is 15. So 15 is printed. So we have observed how this for loop is repeatedly executing and generating sum of first and natural numbers. So both the functions are for same purpose, but the approach of solving a problem or writing a function is different. This is recursive and this is iterative. So that's all in this video. Now let us discuss the problem finding factorial of a given number. So for this also we can define a recursive function, and even using iteration, that is using loop also we can write it. Let us first of all devise a recursive function for this one. So first I will define what does it mean by factorial of a number. See, factorial is represented with this symbol. So this means factorial of n means 1 into 2 into 3 into goes on to n. So it means factorial of 5 is 1 into 2 into 3 into 4 and multiplied by 5. So this will be 120. If I multiply all these things, I'll get the answer 120. So for n, I have to continue up to n. So for 5, I continue till 5. For 10, I should continue till 10. So just like sum of first and natural numbers, this is multiplication of first and natural numbers. That is called as factorial. And even I'll tell you one more thing, that 0 factorial is also possible and its answer is 1. So even 1 factorial is also 1 and 0 factorial is also 1. So both the results are 1. Now let us define this recursively. If I say fact of a number n is 1 into 2 into 3 goes on up to one more term I will include, that is one more number, n minus 1 into n. So in this, if I observe factorial of a number from 1 to n, this portion if I take, this is factorial of n minus 1. Yes, this can be written as factorial of n minus 1. So factorial of n is a factorial of n minus 1 multiplied by n. If I multiply that with n, then I get the result, that is factorial of n. So this can be defined recursively. Factorial of any number n is factorial of n minus 1 multiplied by n when n is greater than 0. When n is equals to 0, means for 0 also answer is 1. So return 1. That's it. So this is the recursive definition. And once you have a recursive relation or mathematical formula, then directly you can convert that recursive formula into a C++ function. So let me write down a function for this one. Integer factorial of n. If n is equals to 0, return, when it is 0, return 1, return 1. Else, return this one. So return factorial of n minus 1 into n. So the function, writing a recursive function is so easy, you can directly convert a formula into recursive function. Now same function even we can write using iteration, that is loop, right? And this is using recursion. Now, it is more similar to sum of first and natural number. If you remember in the previous example, we saw a similar function, only the difference was here it was plus, and one more difference, return 0 was there instead of 1, because the multiplication is there, so it should be 1. So the function is similar. Now, if we do analysis, the analysis will be same. The size of the memory required depends on the value that you're passing. If you find function of 5, that is factorial of 5, then it will be making 6 calls. So the height of the stack will be 6. So the amount of memory consumed is order of n, and the time, number of calls depends on the value that you're passing. Like for 5, it will be making 6 calls. So again, it is order of n. Just in the previous video for finding sum of first and natural number, we have done similar analysis. So I want to avoid analysis here because already we have done analysis for this one. So analysis is same. Now writing a iterative function for this one is a student exercise. So you can write down the function by yourself. So that's all about a factorial of a given number. In this video, we will see a function for finding factorial of a number. I will show you recursive function as well as iterative function. So first let us write recursive function for finding factorial. Function takes parameter n. If n is equals to 0, then return 1. Else return factorial of n minus 1 with n. Inside main function, I will take a variable r to get the result of that factorial function. Let us find the factorial of number 5. The answer is 120. We already know the answer. We should get the same result. Display r. I will run the program. We should get the output 120. Yes, the output is 120. It's a factorial of 5. Let us check factorial of 4. It should be 24. Yes, it is correct. Let us check factorial of 0. What the result will be. It is 1. Let us use a negative number here and see what the function will do. Factorial of minus 1. See, when the value of n is minus 1, then it's not 0. So it will be calling itself again and again, minus 1, so it's minus 2, then minus 3, minus 4, goes on. So actually it has gone into infinite calling and terminated. So you can see total how many calls it has done. 262054 calls it has done. Then why did it stop? Because of stack overflow. So if a recursive function is going into infinite recursive calls, so at one point it will terminate because of stack overflow. System stack has overflown, so it has made so many calls. Factorial is not defined for negative numbers. So if you want to avoid this recursive call, so then here you can write a condition to stop the function if the number is negative. Now I will write an iterative version of factorial. I will call it as ifact. It takes a parameter, and for finding factorial I will take f, that is initialized with 1, and also we need a variable I for iteration. Using for loop, I assign 1 onwards and I less than or equal to n, I plus plus. Then factorial is multiplied by I. So I will be taking different values from 1 to n, and it will be getting multiplied by f every time. So this will be multiplying just like 1 into 2 into 3 into so on to n. Then finally return f. F is having the result. And here inside main function I will call this I factorial function, and I will pass the parameter as 5. Let us run the program and see what the output will be. It should give output 120. Yes, output is 120. Let us debug the program quickly and see how the values of f and I are changing in this iterative version. So you can observe this watch here, watch this portion where the values of fi will be changing. I will continue execution. It will enter into factorial function. Now the variables I and f both are there. I is 1, so 1 multiplied by f is also 1. Then I becomes 2, multiplied by f becomes 2. Then I becomes 3, multiplied by f becomes 6. Then I is 4 is multiplied 24. I is 5 is multiplied 120. I becomes 6, then it will stop. And come back to main function and print the result. So end of program. So that's all in this video. We have seen recursive as well as iterative version of factorial function.